Okay.
Okay.
Shall I?
Hello to everybody. Today we have a new seminar with our great lecturer Alexey Litvinov from Moscow, and he will talk about integrable structures in conformal field theory and of how it's related to affine Yangians and probably Bethe ansatz equation. And we can start.
Yes, thanks a lot. Thank you for inviting me and giving me an opportunity to talk in your seminar. So I will share with you my view and understanding on this topic, as you see on the screen. Why I think it is interesting, because it belongs to intersection of different subjects, mainly integrability, in a wide sense, conformal field theory, and Bethe ansatz approach, which usually appears in spin chains, in studying of spin chains, but miraculously it appears when one tries to diagonalize integrals of motion in conformal field theory. I will not go into like a popular introduction. I will just go to the topic, okay? And by the way, we will see how all the stuff appears. So let's start. So a convenient way to think about the problem, which I will be studying, is to have in mind two-dimensional Toda field theory. So it's not a quantum mechanics, it's two-dimensional classical quantum field theory, Euclidean. So phi is a collection, is an n-tuple of bosonic fields, and can be arbitrary. And so this is the kinetic term and the perturbation, exponential perturbation with some vectors alpha, which are given. And so if the number of the exponents here is concise with the length of this vector, the size of, if you wish, the size of the target space, then you can easily show by classical arguments that this theory is conformal invariant, meaning that it is scale invariant and also invariant under local conformal transformations. Up to some technical details that you need to add what is known as dilaton field, but whatever. But for special, so it is just conformal invariant for any values of alpha. But for special choices, there's just a distinguished set alpha such that the conformal algebra gets extended to what is called, or usually referred as W algebra. I should say that the total classification of all possible alphas such that there is a W algebra is still undone. So only partial results are known. Let's just simplify things and think of that my theory is not just of this form, but it also shares some kind of semi-classical behavior. That means, sorry, do you see my pointer when I roll it? Can you see my mouse pointer? Sorry, can you see? Yes.
Yes.
I see. Thank you. So I will think of it like that my alphas share the semi-classical behavior. So that means simply that all of them are proportional to some b, which is small, and then you can treat b as like a square root of the Planck constant. But that's not necessarily. But for simplicity, let's assume that we have this. This type of behavior, and then I think it can be proven that the vectors ER should be proportional. It depends on how you absorb the B. Should be proportional to the simple roots of some simple more generally semi-simple, but it's not to consider simply algebras of a given rank. Okay, so let's proceed. We will be interested in what is called affine perturbation. So we add another root. I will call it alpha n plus 1. And so if I just pick it randomly, then basically it breaks all my nice W symmetry all down to like just top on Carré. But again, it was pioneered by Sasha Zamolodchikov that you can tune this perturbation, find a special perturbation in such a way that some part of the W algebra, in some special sense, so some part of it gets survived. And it's not, I mean, after you deform the theory, it's not the conformal symmetry, but some infinite symmetry, meaning that you have infinitely many integrals of motion. So what is important that these integrals of motion are perturbative in lambda. I will treat lambda as this perturbation parameter, and I will consider perturbations. These perturbations usually correspond to asymptotically free theories, meaning that lambda gets small in the UV, and then you can expand. Presumably, you have local integrals of motion, which is important, and they admit the expansion of small lambda. And this way, I mean, S naught, your conformal field theory actually defines your...
Can I stop?
Yes.
I'm sorry.
Yes, go ahead. Yes.
Poincare symmetry, what do you mean? Which Poincare symmetry?
Yeah, I mean,
symmetry. What is this?
I mean, just translation, rotation, awareness. Sure, all other
Just
symmetries.
Lorentz Poincare group.
Yeah, no. Lorentz Poincare group. Yes.
Okay.
Yes, but so here's the logic. So S naught defines you some W algebra. I will go into details on next slide, and then so think of it as a point. You have a map. You have a map of field theories of n bosonic fields, of a map of interaction. On this map, you have a point in which you have an extended conformal symmetry, some extended conformal symmetry. It is coded by the set of roots alpha. And then you pick a direction, special direction. This direction is called alpha n plus 1. And the special direction defines you an integrable system, which is perturbative in lambda. In particular, it has a limit when lambda is 0. So this special direction picks you a special integrable system inside this W algebra. And this is exactly the whole this is exactly the setup which I will be studying today. Okay, let's go to example. So the most well-known example is it's called periodic Toda, or SLN or GLN Toda. Yeah, sorry, I have to mention about that. This program has been, the studying of such integrable system has been initiated by Bazhanov, Lukyanov, and Zamolodchikov, starting from 94. But I will use another approach. But in principle, I will compare my results to the results of these authors. So my approach is based on affine Yangian symmetry. So let's just consider the simplest case of closed Toda chain. Okay. So you see there's kind of cyclic structure here of these interactions, and you can recognize the first n-1 roots as being simple roots of SLN, and the last root is affine. So let's just drop, for example, the last root here, the last exponent here. Then it is well known that this theory is conformally invariant. Moreover, it is invariant under the W algebra, as I said. So this W algebra can be conveniently encoded using this mu-Rogel-van-Dicke transformation. So we have this like in elementary factors here. So just expand this differential operator and picks the coefficients in front of given differential polynomials and the monomials, basically, and you will get what is W currents. Usually people ask the question that this theory seems to be interacting, and here in the form of in the Gelfand-Dicke transformation, I mean three fields. And the answer is the following. First of all, on the level of algebra, then you just write the commutation relations whatsoever. It doesn't matter either. I mean, you can represent it by the three fields. The tricky point is to study correlation functions. So, I mean, having this algebra as a symmetry of this theory doesn't mean that you can compute correlation functions in this interacting theory using these three fields. You need more. But today, I will just stay on the level of algebra. That's why, for me, this theory behaves as a free theory, which is not the case, of course, once you try to compute correlation functions. But for simple things, like for on-shell data, like the spectrum, for integrals of motion, it doesn't matter, okay? So Q here is the usual Liouville notation. Q here is a B plus B inverse. And probably I will already give you a glimpse of intuition here. So the Gemura-Gelfand-Dicke product, so phi 1, phi 2, etc., all of them are bosonic fields. So each of them represents the Heisenberg algebra, but they commute for different indices, right? But these like brackets do not commute because they contain differential operator. Let's think of each of these. Sorry, I will draw it using my mouse, so it will not be very nice. So let's think of each of these factors as following. It's just, I'm sorry, it's like a R matrix, basically better to say Lax operator, which so that like two directions. The straight line corresponds to differential operators, and the like curly line corresponds to phi. It's supposed to be phi. So these guys are multiplied like this. Yeah. I will return to this picture later.
Do we know any commutation relation between W's? Does they commute?
No, they do not commute, of course, but they form like, let's call this W algebra. You can compute it from here because you know everything. I will go to these relations further, but it is very explicit because you can expand, compute W's. You know how to commute, how to derive commutation relations for phi's. That's why you know how to derive commutation relations for W. And I should say, I mean, if you think of it in general, it is not that important to have like explicit commutation relations. I mean, of course, for practical things, it is important to have them, but you can define the algebra without basically defining the commutation relations. For example, I mean, one way to define W algebra, many other algebras probably, conformal field theory is to define them as commutants or centralizers of certain set of screening operators. But well, in this particular case, you have explicit commutation relations, but they're not that not that not that important for the whole construction. It's important that you have them, but the explicit form is not that relevant. Okay, so what I did, I just dropped the last exponent here and presented the W algebra. Yeah, probably I should say that. So yes, go ahead, please.
Can I ask a very stupid question? And these bosonic fields, phi, They
Yeah.
commute or not? It
They-
is a
They commute among themselves, but each of them is just ordinary bosonic fields, meaning that I don't know. I will show this later. The OP operator product expansion is contains the poles of second order. So they just each of these guys is just generates the Heisenberg algebra.
Oh, okay.
All right. So what I did, I dropped the last. I wanted to advertise what is known now as a probabilistic approach to basically to Liouville theory, but also to Toda theories. And in a sense, this formula that it can be proven by probabilistic methods that this theory with the last exponent dropped has exactly the symmetry, which is encoded by this Muir-Gilfandicki transformation. So it's not just a physical statement, it has been proven by mathematicians recently. So let's proceed. So I dropped the last exponent, but there's no preferable choice. I can drop any other. For example, let's drop the first one. It is clear that there is a symmetry, right? So when I dropped the first exponent, what has changed? I mean, the only thing which had changed is the order of fields. So before I had n and minus 1 to 1, and now the last bracket had been moved. It became first. It is obvious that these two different W algebras, they are isomorphic, and isomorphism is very simple. You just do this like long cycle permutation in all formula, and just by symmetry arguments, it is clear that if it is not obvious that they exist, but if local integrals of motion exist, you remember that logic, that local integrals of motion is the things which survive under perturbation, and they have a limit in the UV. When I just switched off the perturbation, there's some signs of local integrals of motion still in W algebra, better to say in universal envelope. And it's clear from what I just said, that the integrals of motion, local integrals of motion, should belong to intersection of universal envelope and these two W algebras. And this is basically a constructive way to find them. And you can find them on, this is two examples. So I1 is just, everything is holomorphic in my story. Sorry, I had to say it before. All of you know that in conformal field theory there is a holomorphic factorization. I'm considering only one chirality. So A1 is just the L naught and energy, if you wish. But you have also integral of spin 3, of spin 2. It is integrated. It is the integral of the density of spin 3. So H's here are nothing but the weights of first fundamental representation. So this is how you define the integral system, okay? And already from here, you can notice that, as I said, these two W algebras, which I just showed, they are isomorphic, and in particular, if there exists an intertwining operator, I'll call it T1. If it exists, then it itself an integral of motion. It's just obvious because any integral of motion belongs to the intersection, and from this formula that it intertwines two W algebras, it immediately follows that T1 will commute with local integrals of motion. And that's why it is clear that the operator, which does the simplest permutation, basically just permutes two factors in the Muir-Gilfandicki formula, is very important. It has been noticed in a seminal paper by Mavlik Okunkov that this operator, let me call it R, with two indices I and J, which does exactly this. It permutes two factors, two neighboring factors, it is an R matrix. And in terms of this R, my operator T1, I will call it Yangian operator, is just a lone cycle permutation. It just does this job. It permutes one all over the set 2, 3, etc. Okay, it follows immediately. So let me draw again to explain. So this equation here, you can think of it. You remember? I don't remember how which line corresponds to what in my previous drawing, but it's supposed. So this equation, you can think of it. As follows. So right, you multiply two Lax operators over the Corley direction, which is my differential operator, and then like intertwine them by the R matrix. So here, so this thing is the R matrix. It does not differentiate things because R matrix is just it is built of straight lines, so it just knows about the phi's and the operators, Lax operators, they multiply it as differential operators. Okay? So this is the way how the R matrix is defined. It's probably not very, I mean, usually in like this R matrix business, R matrices are defined from other perspectives, but here, I mean, for me, it's very convenient to think that the definition of the R matrix is this formula.
Alusha, what question? This
yes.
T1, yes, this is very close to be something the momenta, right? Something. Because this is making some transposition from the point 1 to the from the changing. What is the difference between W tilde and W? Yes, right? Only the change of W one you push to the end, right?
Yes, exactly.
Now the one is making this opposite direction, making something, right? Making something opposite direction is pushing opposite to T, the one to the operator something. T1.
Yes,
right?
but you know how to say there is a it's not the momentum from the point of view of this field theory, right? Because it has nothing to do. It moves how to say, it moves your fields in this auxiliary space.
Yes, right, exactly.
So it is a momentum from the point of view of a spin chain, but it's not the momentum.
Yeah. True,
yes.
true.
Okay.
But why you call this замолочек of the Konishnik?
You will see later. Yeah, you will see later. Later you will see. Yeah, because it is a part of Konishnik замолочек.
Can I ask another stupid question? And what is known about this R matrix? Can you construct it in explicitly or in some way? Somehow?
Yes. Something is known. Yeah, first of all, let me like emphasize this R matrix is written in some very special representation, right? So it's kind of you should think of it as a R matrix which intertwines two spin 1/2 representations in of SL2. So compared to SL2, which is known, of course, explicitly, here you have, you will see later, you have first of all, it's an infinite dimensional matrix. You can compute any given entry depending on how much effort you invest. There are some explicit formulae. One of them belongs to Andrei Smirnov, which is, but it is explicit. It's given in terms of infinite product, but it's still, how to say, it's still, when you compute things with it, you still have to expand this product and you still have to do some job, right? But as I will convince you later, you don't need to know all the matrix elements, in fact. You need only some of them, or only lowest level entries. Of course, they all rational functions. This is rational matrix, okay? It's a Yangian. You can, so in order to obtain things which I will obtain, like beta ansatz, you will need only few matrix elements. Yes, there are some expansions for like large spectral parameters, and also there's some representation again through other things, like through screening operators, which are also, so there's kind of explicit formula, but wouldn't say it is explicit. In fact, it is just explicitly expressed this art through other object, which is not that explicit as you can think. So, but there is also some, there's a trigonometric version of this R matrix, which is R matrix for toroidal algebra. And I think there are some also explicit representations, also given some infinite products, probably infinite sums or so on, but I will not use none of this. Probably I should.
Formula, it's type Koroshkin-Tolstoy formula or something like this?
I believe it's similar, but yeah, I'm not an expert on this thing, sorry.
Okay, thanks.
There's some formula of Andrei Nigul's also. It also it's different from Andrei Smirnov formula, but also I didn't check it and didn't basically get myself familiar with this. Sorry. So let's proceed. So R is our matrix. So it satisfies the Yang-Baxter equation. It follows immediately from the defining relation of R, just because R the R matrix appears as an intertwining. It appears as an actor in the RLL equal LLR relation. Okay, that's why it satisfies Yang-Baxter, which you all know. And so just immediately, let's just consider the spin chain on n sides. So yeah, I should say that R depends on the parameters, which are, who are these parameters? These are parameters of the, I'm considering the Fock spaces, the highest way representations of Heisenberg algebra. They are labeled by highest weight parameters U. You can easily show that the R matrix depends on the difference of these parameters. Next, you will see that is a rational function. And so you may consider what is, you should compare it with the spin chain on n sides, and you take a trace of the auxiliary space labeled as 0. Here you have n-dimensional quantum space, and U's are what you would call inhomogeneities in the spin chain business. There's a trace here, traces. There's a problem with this trace because it diverges basically. Yes, sorry, something is written here. Yeah. Here I just said that the Nizhny Zamolodchikov, the KZ. Oh, sorry, it has been paused. Nizhny Zamolodchikov operator appears. This is a standard thing that it appears as a special point of the transfer matrix. Because at zero spectral parameter, the R matrix is just permutation, and then you can find that T of U1 is just T1, which we had before. Here I also explained that in fact, the trace diverges because you sum over infinite dimensional auxiliary space, but you can kind of fix this divergency because you can take the weighted trace instead of just tracing the matrix. You can trace it with q to the power L naught, and L naught just measures the level. So just the total level on your Fock space, and it can be shown very easily that this operator here plays the role of the twist operator in the spin chains. It's like q to the sigma 3, total sigma auxiliary sigma 3, and so, it doesn't violate the integrability. The integrability, sorry, I had to say it before. Integrability means that the transfer matrices commute for different values of the spectral parameters. So this introduction of this Q does not violate the integrability property. Okay. But of course, it modifies your integrals of motion. They become not quite local. I will call them semi-local, meaning that locality is broken mild. It's mild broken of locality. So here you see the first two representatives of the infinite commutant family of local, semi-local integrals of motion. You will see that they contain this operator D, whose Fourier symbol is this non-local thing. So it's kind of composition of the derivative and of this geometric series, right? But it's not, I mean, it's still kind of derivative. That's why I call it semi-local. Of course, the locality is broken. And if you try to find the corresponding classical integrable system, you will find it in the literature. Integrable systems of this type are known as intermediate long wave equations.
Sorry, do you say that you have nothing more but quantum version of Benjamin Ono or EL wave if you want? So it's this D, it's nothing more but Hilbert transformation on the circle. Is it true?
Hilbert transformation corresponds to Q equals to 0. Because, so let's say this operator becomes modulus of K, right? Because then Q is 0. If like this ratio is 1 if K is positive and -1 if K is negative, right? Because then you send Q to 0, and that's why it becomes just the modulus of K for Q equals 0. And in that case, it is a Benjamin Ono, as you said. If Q is not equal to 0, then it is intermediate long wave. The limit, local limit corresponds to Q goes to 1. It's kind of tricky to do this limit, but in that case, you will obtain KdV-like integrable system. So you have rank n integrable system, which there are two parameters, basically three: quantum parameter Q or B. I mean capital Q. It's like a Planck constant. It's your quantum parameter. Then you have the rank of your system, which is n, and you have this parameter Q, small q. So then Q goes to 1. It corresponds to so it's a, I don't know, it's a series. I don't know exactly the name of this integrable system. It's a series which starts with KdV, then the next representative is called Boussinesq integrable system, and then there's something else. So it's, you know, matrix KdV integrable system. And then if Q goes to 0, it becomes Benjamin Ono integrable system. It coincides with it for rank 1. When only one field. In general, such integrable systems were, I think they were discovered by Lebedev and Radl, as far as I know. In both cases, in Benjamin Ono and also for intermediate long wave. So it's kind of matrix generalization of KdV. What is remarkable about these integrals of motion? They can be simultaneously diagonalized. They can be diagonalized without any without any Yangian matrix whatsoever, what the Yangian symmetry, which I will present you soon, does is the Bethe ansatz equations. So I believe that most of you know what the Bethe ansatz equations are. Let me just say quickly that you have, in order to find the spectrum of your integrals of motion, you have to solve a set of algebraic equations, which you have a bunch of auxiliary coordinates xi's. The number of them is your level. Everything commutes with the level, with the total energy. So total energy is measured by the number n. It is a number of magnons in this imaginary spin chain, okay? So if you want to diagonalize your integrals of motion, which mutually commute, so they have the simultaneous spectrum, if you want to diagonalize them, first you pick the level, then you have to pick exactly this number of auxiliary variables x's, beta roots, then you solve algebraic equations. So here I already introduced Nekrasov-like parameterization of the parameter b. So instead of b and b inverse and b plus b inverse, I will use epsilon 1, epsilon 2, and epsilon 3 such that the sum is 0. Just convenient rescaling of all things here. So you choose your level, choose your axis. Then you have to solve this transcendental equation. Should be q here. I don't see if, yes, there is a q, the twist parameter on the left-hand side. If some of you have tried to solve these equations, you know that this is a very complicated task, but suppose you accomplished it, you solve and you found a solution, then your local integrals of motion, their eigenvalues are symmetric polynomials in the Bethe roots. This is the statement. So let me proceed. It's just still my introductory part. So what I just advertised is that affine GLN Toda type theory, which, as you may guess, is coded, can be coded by this type of fine Dynkin diagram, is governed, I mean, the spectrum of local integrals of motion, this theory is governed by the Bethe ansatz equation, which I just presented before. So you should think of it as like each circle here is a presentation of your fundamental algebra. In our case, it's just GL1 or Heisenberg algebra. Have a tensor product of it. And so if you have two circles joined by an edge, that means they have non-zero scalar product. And that means that for each edge, I associate exponential operator. And so what we just seen is that the spectrum of local integrals of motion is given by Bethe ansatz, which I presented. Yeah, I should say that this picture is very special case of more general situation. So imagine that you can have like each, let me call it atom here. In each atom, there is a representation of some algebra. I mean, think of that in each node, in each atom, you have a representation of Kac-Moody algebra of some rank and of some level. Then each node, which connects them, gives you some interaction between these two algebras. That means that you insert some exponential-like operator. And there's also, since you closed everything, closed with meaning that you consider the closed spin chain, you have introduced some twist parameters. And this is very general situation. I'm considering very special one, but in principle, the affine Yangian business provides you a lot of integrable systems where the atoms might be much more general things than just representation of Heisenberg or GL1 hat, and a lot of interaction between them. But not only this, because you can also consider integrable systems with a boundary. I mean, this boundary is not the boundary from a field theory point of view. It's a boundary, if you wish, in the target space. It's a boundary from the point of view of the imaginary spin chain we have. I will not go into details, but probably most of you know that Sklyanin suggested that in order to find integrable boundary conditions for the spin chain, you have to solve KR equation, and if you solve it, each solution would, I mean, from our point of view, each solution would provide you some, again, some Toda field theory with the W algebra and with distinguished set of integrals of motion. So restricting ourselves to the case which we consider just one bosonic field in each node, and moreover, all of them are semi-classical, you will find all possible twisted and non-twisted affine diagrams, excluding exceptional ones. So it's the story. So, I mean, I'm explaining how general the story is. And again, you can, I will not provide you the details of this derivation, but again, using the machinery of Bethe ansatz and so on, you can derive Bethe ansatz equations in this case as well. So for all possible, so in this case, boundary conditions, they correspond to how your affine diagram ends. So any affine diagram in the middle, it looks like AM. The only difference happens at the ends. There's left boundary condition, right boundary condition. They are encoded in this Bethe ansatz. So this is done in our paper with Ilya Vilkoviskiy. This is just an advertisement. The same thing should exist for any for more general examples. As I mentioned, each atom in this Dinkin diagram might correspond to more general algebra, and this is not has been done so far. Okay, so now about R metrics, about computational relations, etc. So first of all, it's clear from the definition. So you remember that R permutes two Miura brackets. Just follows from this definition that R commutes with the sum of bosonic fields. That means that R as an operator, I remind you, it depends only on Fock variables, not on, it does not differentiate things. So R depends only on difference, half of difference of them. And when you reduce it to the half difference, you can formulate, you can write the defining relation for R in this form. So you have U1 current J, which has the singular, which has an OP of the second order pole, and the coinciding points. Q is our capital Q is our parameter, quantum parameter, and this is the defining relations. It is just this, written in a simplified form. I mean, this star is nothing, sorry, it's nothing bad, but this, the essential part of this defining relation, R equals to LR for very special L, is this star formula. But in order to make it like explicit, we expand everything in terms of modes. When I do this, I assume that all of you are familiar with the creation and annihilation operator. So I'm considering highest weight representation, which is like defined by this formula. So it's some highest weight, which is eigenstate for a zero mode of the current J, and then negative modes. Positive modes annihilate, kill this highest weight, and negative modes generate new states. Then you the relation which I had before can be rewritten in this following form. It's like an infinite set of relations of this form. So you apply like creation operators of such bilinear currents. These are nothing else but the generators of the Virasoro algebra. You have two Virasoro algebras because you have two two possible choices of sign here, either plus or minus. Once you have chosen, this sign is just indicated as an upper index here. So each of these lengths is given by this formula, and you have like this set of equations. If everything is in general position, I mean, if all the numbers which you have here are generic, and I'm assuming this, then this set of equations it's a set of linear equations, has a unique solution up to the total scalar factor, which is, of course, you cannot fix it for a matrix. You can choose it as you wish. It's your choice. But up to overall scale, all the matrix elements of the R matrix can be computed. Here I computed first three matrix elements for you. You can see they all rational functions of the spectral parameter, and they all depend on Q as a parameter. Moreover, you can see that the poles, how to say, they are, you know, the poles are, of course, not the zero, so it cannot be. You see that the matrix elements have some like random zeros, but the poles are in known positions. This is the general instruction. In principle, if you have enough patience and willing to compute, you can compute very deep in the model, so you can compute up to high levels these matrix elements. Okay, but as I said, you don't need, in fact, all of them. You need only a few of them. For example, let us define the Young-Baxter algebra. That's a usual thing. We just start. We have matrix. I explained that it's completely defined, but it's defined in relations. Now let's consider this equation, assuming that L is an operator which acts in some quantum space, not necessarily as it was before, then our quantum space was just differential operators. It can be arbitrary. In that case, this RLL equal LLR relation is a set of quadratic relations between the matrix elements of L operators. So the matrix elements here in this problem are labeled by pair of partitions, because each of L is an infinite dimensional matrix whose auxiliary space is a Fock space. The basis in the Fock space is labeled by partitions. So in my notations, A with a minus mu, the mu is bold, means that I have taken the product mu1, mu2, etc. And I always assuming that this is a non-decreasing set. So mu1 is greater or equal than mu2, etc. So this algebra is nothing but some set of quadratic relations, and you can compute them all in principle because you know how to compute them. Now we do very standard thing. We define the currents, basic currents. So basically I do this. I have some auxiliary space. Now quantum space mean something very general, not necessarily differential operators. And I just pick some matrix elements in the auxiliary space. So H corresponds to taking vacuo. Sorry, hard to draw, but vacuo here is just H. Then you can have like vacuo here and box here. This is almost E, but you have to divide E by H inverse to get what we call E, and F is the opposite thing. Yeah, sorry, I have to say that in my notation, I will always use it. So if I draw this picture, that means that my ket states are here and here. So how to say, I act in auxiliary space, I act from right to the left, and in my quantum space, I act from top to the bottom. Okay. So this is just a definition. I also define auxiliary current psi, which is kind of, well, some combination of homogeneous matrix elements. Yeah, it should be noted also that all currents are expected to be expanded at large U, large values of the spectral parameter. This is our assumption. It holds in all cases where our representation, in all cases where our curly line corresponds to the tensor product of Fock spaces, this is true. So we'll assume that all of them admit this expansion. And I basically treat these currents, simple currents, as a large lambda, large U expansion, always, okay? But of course, because your matrix is infinite dimensional, you have infinite dimensional, you have a lot of what is called higher currents. Today, I will only use 3 other currents. Better to say 6 other currents with also F currents similar to this. By some reasons, which I will not explain right now, they are labeled by three-dimensional partitions. So the 3-dimensional partitions consisting of 2 cubes. And these are defined by these explicit expressions. This is just a definition. Should be sign a definition on top of this equal sign. Okay. So then just from the commutation relations, from the explicit form of R matrix, you can find the commutation relations. First of all, H's and psi's form a commutative subalgebra for any values of spectral parameters. It just follows from Young-Baxter algebra. Moreover, as you can see, like E and F, they together with H, they behave in this exactly the same way as they would do in SL2 case. They just have the same commutation relations. So you might notice that some part of this commutation relation is highlighted by blue. What do I mean by this blue? I will call this local terms. Why are they local? They're local because other terms in this relation are not local. They better say be local. They depend on each, like operator here is a product of 2 operators in different points, but not the blue one. These are operators evaluated at the same point. Why it is important? Because imagine, I mean, these commutation relations should be expanded large U and then large V. Assume that you expanded. Everything here is polynomial. Then, of course, this local term, blue term, it doesn't contribute. The commutation relations which follow from here, they're labeled by 2 indices, I and J. I is a mode of H and J is a mode of E. Of course, this blue term doesn't contribute to the most of commutation relations. It contributes only to those that, say, index I is equal to 0, right? That's why, in most of commutation, they do not appear. The same is for commutation relations between E and F. Here, the functions G are not presented here, G and bar G, because they are on the next slide. So you see that G and G bar are polynomials with 3 roots, okay? Exactly epsilon 1, epsilon 2, and epsilon 3, together with the sign. And you might have the impression that there are poles in this relation. No poles. I just absorb the total polynomial for the 3 in front of this bracket. So altogether, also the polynomial relation within the currents. Another point which I would like to raise, these relations look similar to, people might get confused. They look similar to like OP equations in conformal field theory. This is like, it's not the case. These currents are always non-singular. So once U or V approaches each other, nothing happens. It's just a smooth limit. Okay, so this there's no poles in these relations at all. And all these formulae have to be you thought of them as everything is expanded in large values of U. This is very similar. You might call this algebra, just take it by definition, as a affine Yangian of Heisenberg algebra of GL1. Yeah, better to say that in mathematical literature, by affine Yangian, they mean the subalgebra which is spanned by E, F, and psi. Here we have more generators. We have also H, and the difference, I think it's very similar to the difference between the Yangian for GL and SL. So the difference is by some center, but I will not go into details here. So let's just take this as a definition of the algebra. This is just the commutation relations. But that's not all commutation relations, but because you also need what is called Serre relations. It's a cubic relations of this form. Let me emphasize again. I've derived these equations just from the R matrix which I had before. You can just compute the matrix elements and just show that these relations are hold. The fact that there are no other relations is some, I think, theorem which I don't know if it is proven or not, but yeah, it's very interesting statement, in fact, because you have infinitely many matrix elements, infinitely many relations, but the statement that all of them are follow, in a sense, from these fundamental relations. Okay, so what we just learned. You have an algebra, and we have the kind of Cartan subalgebra in it, spanned by H and psi. Let me say about H. What is H? Let's stress again. So you have like some auxiliary space, and here I have taken just in auxiliary space I sandwiched between two vacuum. What is it? In fact, it's nothing else but the as Andrei said, it's a transfer matrix for Benjamin-Ono system, because it's nothing else but the limit of my transfer matrix, of my twisted transfer matrix Q to the L naught with something. Something is a product of R matrices. When Q goes to 0, because sorry. So Q goes to 0. Because if Q is 0, this trace picks only the contribution from the vacuum. All other states have positive energy. Okay, so H is nothing else but H equals to T of 0. Q equals to 0. So let me consider my goal is to find the Bethe ansatz equation for this algebra. Let me first diagonalize H as a warm-up exercise. I call it zero twist integrable system just for reasons which I explained. I proceed in a very standard way, but still, probably some of you is not familiar with this construction. So suppose I have an eigenvector of my H. Can I construct new eigenvector acting by E? Well, in general, I mean, E acting on lambda is not an eigenvector, because in my commutation relations, I have those local terms. And they violate. So when I act by H on my new supposed to be eigenstate, it's not an eigenstate because of this auxiliary term. But what helps here is that the local term, like the unwanted term in this relation, it doesn't depend on V, on a point where my creation operator E lives. Yeah, I should have explained why E is a creation operator, but I suggest you just to trust me that in a representation, in a right representation, E probably, now I think that probably the name is kind of misleading because usually F is a creation operator, but for some reason I have chosen E to be the creation operator, okay?
Josh, 5 minutes. Okay?
Что? What 5 minutes?
You left. Have only 5 minutes.
5 minutes? I thought we had 2 hours. Only 5.
If you want, we can continue in 2 weeks. In 2 weeks.
Oh, 5
May
minutes.
27. It's okay for you?
No, it's okay for me, but let me. Yeah, sorry, I thought I had 2 hours. So let me try to come to some positive point. Yeah, I think I can. Yes, we can like finish this construction. So zero twist integrable system, okay? So this local term violates this to be the eigenvector, but suppose that lambda is such that that E of V has a pole at some point, which is like given by lambda, by your state's lambda. Then the left-hand side has a singularity, and the right-hand side, only the first term has a singularity, and hence lambda tilde, which is just the integral around those. I assume that this singularity is a simple pole, then the integral around those singularities is a new eigenvector. Moreover, you know the eigenvalue of H just from this formula. Okay, this is just a simple construction, and this way we can diagonalize it very, very easily. So that was the idea. Let me drop this statement, and suppose I'm diagonalizing my integrable system in a tensor product of n Fock models with highest weight parameters x1, etc., xn. Then you can easily find that your Cartan subalgebras, so your current H x by coefficient 1 on the vacuum state, and psi x with this by this combination of by this rational function, and then the vacuum, as I said, is annihilated by F's, and then you can construct generic eigenstate of my zero twist integrable system by just application of the creation operators and picking poles in a special position. So all the poles correspond to what is known as contents of the Young diagram. So each Young diagram starts, well, you have to imagine like a complex plane, C, and there are special points called X, say X1, and here from here, there's kind of coordinate epsilon 1 and epsilon 2. And draw your diagram, Young diagram here. Sorry, I should be drawn here at the angle. Okay, something like this. So here, C is the content of a corresponding cell. For example, the content of this cell here is x1 minus epsilon 1 minus epsilon 1, etc. So you can show that applying E, you will have a pole at that point, and if you take the like repeated residue, you will obtain an eigenstate. This eigenstate I will denote, as you see here, by the set tuple of partitions. You have some number of partitions depending on length of your spin chain, and this is given by this formula. Okay, and I think I can stop here. So what we'll do next time? Next time, we just constructed eigenfunctions Bethe states for q equals 0. Next time, we will proceed and we'll consider case q not equal to 0. You will see next time the construction of off-shell Bethe vectors and how to derive the Bethe ansatz equations from them. So this is the most important picture in my story, which is doesn't belong to us. It's basically Tarasov-Varchenko off-shell Bethe vector, which works perfectly well here as well. So thank you very much. Sorry, I missed the point that the talk is only 1 hour. So your questions are welcome.
Okay, thank you for your talk.